Greetings to all. This is Satish Swaminathan, a PhD scholar working under Professor Raghunathan Rangaswamy in the Department of Chemical Engineering at IIT Madras. This presentation is aimed at providing a peek into the area of prognosis and management in lithium-ion batteries and what we at the Energy Systems Group in SENAI contribute to the said domain. The following aspects would be touched upon during the course of this presentation. We'll start off with identifying the need for prognosis and management in lithium-ion batteries. Next, a brief description of battery management systems will be provided, along with the basic functional aspects of an ideal BMS. This will be followed by an introduction to the fundamental battery states used in diagnosis. Finally, we'll see some of the work that's happening at SENAI in the area of battery research. So, why is there a need for prognosis in lithium-ion batteries? Lithium-ion batteries are undoubtedly the most sought-after energy storage devices, especially for portable and automotive applications. The boom in electric vehicles has further strengthened the demand for lithium-ion batteries. Advantages such as high energy densities, longer shelf life, and reducing costs, to name a few, have been a major reason for lithium-ion batteries' popularity. That being said, lithium-ion batteries do have finite life, beyond which they cannot deliver the desired performance. However, suboptimal usage of batteries could cut down on its life prematurely, which is a major cause of concern for manufacturers of batteries and electric vehicles. Also, battery life cycle estimation involves prolonged experimentation, sometimes extending over thousands of hours and requiring sophisticated equipment. This poses a major hurdle to innovation in battery technology. The difficulty in doing these tests stems from the nonlinearity in the capacity fade. As a result, it's essential to perform the tests at realistic cycling rates, which increases the duration of the experiment. To add to this, the lifetime of a lithium-ion battery depends on factors such as temperature of operation and the usage, that is charge-discharge pattern, among others. All these aspects combined warrant a need for a quick and efficient method for battery prognosis. Let us assume that we've identified the usable life of a battery. That is, we know how long a battery would last before it needs to be replaced. Is there still a need for battery management system? Battery prognosis is generally performed under controlled settings. However, lithium-ion batteries are highly sensitive to changes in operating conditions, especially the temperature, terminal voltage, and charge-discharge rates, among others. Operating lithium-ion batteries outside the optimal conditions affects the performance and life of batteries and could also lead to safety issues. The adjacent figure shows the safe operation window for lithium-ion batteries in terms of temperature and voltage, and the potential failures in case of operation outside the window. Thus, there is a need to keep the operating conditions within the safe window during usage in order to ensure safe and reliable performance, which necessitates the need for an onboard BMS. A battery management system is basically defined as any electromechanical system that is capable of managing a battery to ensure safe and reliable operation. As discussed earlier, battery management systems are a necessity when it comes to lithium-ion batteries, especially when considering high power and energy-intensive applications such as electronic vehicles and grid storage, which uses multiple cells arranged to form bigger battery packs. Thus, there is a need to regulate temperature and voltage of each individual cell and also optimize the charge-discharge profiles, among others. The key responsibilities of a BMS are to operate the battery within specific conditions so as to guarantee performance, safety, and longevity, to ensure that the battery is capable of delivering the power demands, to protect the cell from damage, both physical and otherwise. A BMS manages batteries by monitoring them, estimating and controlling their states, balancing the load on individual cells, and regulating the operating conditions so as to guarantee their safety and longevity. The adjacent figure shows a concept on-board BMS on a lithium-ion battery pack. Here is a functional block diagram of a typical battery management system. The extent of features available in a BMS may vary depending on the requirements. It would include facilities for monitoring battery parameters down to the individual cell if possible, diagnosis and estimation of battery states and faults, data collection and storage, control of batteries' operating conditions such as terminal voltage, temperature, charge-discharge profiles, etc. It is also inclusive of sensors and actuators that will be used for monitoring and control respectively. Battery states are metrics which help understand the condition of a battery. The fundamental battery states are state of charge, state of health, and state of function. State of charge is a measure of the remnant energy in a battery. It is the ratio of energy remaining in a battery at any given instant to that when it's fully charged. State of health reflects the current health of a battery when compared to a fresh one. It gives insights into the remaining usable life of a battery. State of function is a measure of the ability of a battery to successfully meet the power demands placed by the load. Consider an example. You have just bought a 10 amp hour battery which is fully charged and you use it on your laptop. 10 amp hours in this case is the rated capacity of the battery. Now, you use your laptop for some time. That is, you discharge the battery until the battery indicator on your laptop shows 50% charge remaining. It essentially means that 50% is the state of charge of your battery. This would mean that you have roughly 5 amp hours of charge left. Now, if you were to recharge it back to 100%, one would assume it would always hold 10 amp hours of energy, wouldn't it? Over time and repeated use, the capacity of batteries decrease. Consider it as some sort of leak or dent in a fuel tank. Thus, the battery, which was originally able to hold 10 amp hours of charge, is now capable of holding only, say, 9 amp hours. The other 1 amp hour of capacity is said to be lost or faded. Now, if you recharge the battery until it read 100% on your indicator, it would only contain 9 amp hours of charge. This is the current or instantaneous capacity of a battery. Now, if you were to discharge your battery again to 50% SOC, it would essentially mean that you have only 4.5 amp hours of energy left. This loss in capacity is considered while analysis of state of health. Thus, state of health gives the extent of degradation in a battery when compared to a fresh one. For most commercial applications, a 20% loss in capacity is considered to be the end of battery life. However, state of health analysis should also take into account the self-discharge rates, the cell impedance, physical damage, faults, etc. while determining the usability of a battery. Now assume that the laptop is rated for 50 watts at 10 volts. This would be the peak power demand on the battery, and the corresponding peak current would be 5 amps. However, the terminal voltage of the battery would drop when substantially large currents are drawn, and if the terminal voltage falls below a cutoff voltage, the battery will not be able to power the device. The ability of a battery to meet the power demands without interruptions is given by the state of function. In essence, it is an indication of the robustness of a battery. This flowchart shows the relation between the 3 battery states and the inputs that the respective estimation algorithm takes in and the results that they give out. A multitude of tools and techniques have been developed for estimating battery states, each having its own set of merits and demerits. Depending on the application, one could pick a particular technique or a combination of techniques. Here is a list of techniques and methodologies for estimating state of charge, state of health, and state of function. There is, however, one tool that can be used to estimate all these 3 states simultaneously, and that is battery impedance measurement. Impedance measurement is one of the most important diagnostic tools used in electrochemical systems. Impedance can be defined as the opposition that an electronic component, circuit, or system offers to an alternating current. It arises from the combined effects of ohmic resistance and reactance in a conducting medium. It has the ability to provide insights into the kinetics of electrochemical processes that occurs inside batteries, including various side reactions that are detrimental to battery health. Each cell in a battery could be modeled using an equivalent circuit having a certain impedance associated with it. The impedance of a battery varies in accordance to any electrochemical process occurring inside. Researchers have shown that the impedance profile of a battery could be used to estimate the state of charge, state of health, and in turn, the state of function of the battery. Furthermore, literature shows that impedance profiles could also be used to estimate cell temperatures. Electrochemical impedance spectroscopy, or EIS, is the most widely used non-invasive diagnostic tool for obtaining impedance profiles. EIS provides the impedance of a system over a spectrum of frequencies. Thus, it allows for separation of process in the frequency domain. However, conventional EIS techniques are time-intensive and requires bulky equipment, thus rendering them unfit for online or real-time applications. In an attempt to reduce the time taken to obtain impedance profiles, we at SENAI have developed a novel technique, namely the phase-shifted chirp analysis, which utilizes chirp signals instead of conventional sinusoids to obtain impedance profiles. The chirp signal differs from a conventional sinusoid in that the instantaneous frequency in a chirp signal is a function of time. Essentially, the signal has a different frequency at each instant in time. This allows one to pack a higher bandwidth signal in a very short duration. Depending on how the frequency sweeps over time, chirp signals can be either linear chirp or exponential chirp signals. The phase-shifted chirp analysis technique offers another striking feature, that is, its ability to use transient information to estimate impedance. In conventional EIS measurements, however, the transients are allowed to die out before the actual measurements are taken, which adds to the time taken for obtaining impedance profiles. Phase-shifted chirp analysis has been shown to be more than 10 times faster than conventional single-sign EIS. A typical chirp analysis procedure is explained in the following section. It starts with the injection of a couple of short-duration phase-shifted chirp voltage or current signals into the system under test. The response of the system to the chirp is then measured as current or voltage depending on the input type. The input and its response are used in the chirp algorithm to compute the impedance profile. A couple of approaches for estimating battery states and identifying faults that are being studied at SENAI have been explained in the following section. The first is based on an empirical approach. It involves obtaining impedance profiles of batteries under various states of charge and health. Based on the impedance profiles obtained, corresponding equivalent circuit models for the battery are generated. Now, a relationship is established between the various impedance profiles, circuit parameters, and the battery faults and states. Finally, based on the relationship developed, impedance measurements are used along with adaptive techniques to estimate battery states and faults. The second approach is based on developing first principles models and using it in estimating battery states and fault identification. It starts with developing a basic model of the battery from first principles. The basic model would be able to capture the fundamental operating mechanism of a battery. On top of this basic model, various capacity fade and failure mechanisms are incorporated based on the physical process. Then, the battery states and faults are described as an interaction between various mechanisms operating on the battery. Finally, these descriptions are used to estimate battery states and identifying faults through adaptive techniques. Some of the objectives at SENAI in the area of battery research are as follows. Identifying key prognostic features that are exhibited by lithium-ion batteries. Developing empirical and first principles models for capacity loss and faults in lithium-ion batteries, which in turn could be used in developing predictive algorithms to estimate lifetime of batteries without the need for extensive cycling. The above efforts are aimed at developing a quicker and effective technique for battery prognosis, suggesting means on extending battery lifetime and coming up with an extensive in-house battery management system. Thank you.